Thank you. It's great to be here, and I want to talk with you about our planet, our industry, and our future. So I think everyone in this room needs to pay careful attention to what is a stark and a little bit scary future for all of us. But I think all of us in this room, if we put our heads together, can help be part of the solution. I'm going to talk about the tidal wave of power consumption on planet Earth. And if you look at the history of our world, beginning in the 1800s when firewood, timber, was the main source of energy, moving to the start of the Industrial Revolution in the 1800s when the steam engine was created, when we started to build railroads in the 1850s, what you can see is the consumption of energy globally each year began to rise, not surprisingly, along with population. The first oil well was drilled in Pennsylvania in 1859. Natural gas became possible to transport in the 1920s. So you had a railway system and you started to have pipelines in countries all over the world. But what's surprising and what is called often a tsunami is that over the last 40 years on our planet, our 8 billion people now are consuming 180,000 terawatt hours of energy. In fact, let's have a little audience participation. I want us all to say 180,000 terawatt hours. Ready? 1, 2, 3. 180,000 terawatt hours. You can do better than that. Let's say it again. 1, 2, 3. 180,000 terawatt hours. That's what planet Earth is doing. And it's easier to say 648 exajoules. So let's say that. 648 exajoules. Ready? 648 exajoules. Now, this is an important number because that's the amount of energy we consume on planet Earth as of last year, 2023. And at Stanford University, where a very famous venture capitalist, John Doerr, has put hundreds of millions of dollars in and hired a new dean, Arun Majumdar. Arun Majumdar calls this the energy consumption tsunami. I'm calling it a tidal wave. Both things are bad. We've doubled the energy consumption in the last 40 years on planet Earth to amazing amounts. And this is before the AI revolution. When you look at where this consumption of energy is coming from, what you see are staggering population growths. First of all, look at Africa. Africa has grown from about 500 million people to 1.5 billion people on planet Earth. Remarkable population growth. You can also see China and India have grown in the last 40 years as we've doubled our energy consumption in a remarkable way. You can see that Asia Pacific, excluding China and India and Japan, have gone from you can see in the orange curve, about 700 million people to now looking at about 1.3 billion people. That's a doubling. Yet you see the populations of Europe, US, China, Russia, flat or in some cases decreasing a little bit. So we've had enormous population growth, particularly China, Africa, India, and Asia Pacific, China and India. And if you look at the map of the energy consumption, this is a logarithmic scale. Darker means more energy consumption in terawatt hours per year. You can see from the left in 1983, 40 years ago, to the right, 2023, over the last 40 years, you can see the dark parts of planet Earth where energy consumption is really ramped, not surprisingly, the US, India, China, but you can also see darkening in Africa. You see South America starting to consume more energy. You also see the Asia-Pacific region also increasing in energy consumption. Now remember that 648 exajoules per year energy consumption? When you look at the amount of energy consumption happening around the world, what's remarkable is the growth of China. If you look at the China energy consumption in the last 40 years, you can see that around 2000, it started to really ramp up to now about 180 exajoules, more than 25% of the world's energy consumption. And you can see remarkably in Europe and in the US, where policies in the 1980s began to curtail energy consumption and started to look at more conservation of energy, you can see that the energy consumption in the US and Europe has remained relatively flat. Of course, their population has been relatively flat, but you can see with the growth of all the industries that consume power, the focused policies to reduce energy waste has created big dividends in developed countries that put their energies there. You can see that energy consumption is directly related to carbon dioxide emissions, CO2, greenhouse gases, which create an environment in the atmosphere that keep the heat in and raise the temperature of the globe. And you can see directly in proportion with the energy consumption of these countries, you can see that the greenhouse gas emissions attributed to these countries increase lockstep. What's amazing is you can see the growth in the China, in Asia-Pacific ex-China and India, and you can also see in the pink India growing. These are the countries that right now, with massive population growth, are also experiencing a huge amount of the carbon dioxide emissions that affect the entire planet. Now, this is a real thing, and in the US, this is politicized. You know, whether you say climate change or global warming is a bad term by some politicians, but climate change is the kind of universally accepted language, and it's not arguable. It's a fact that our carbon dioxide emissions have gone up dramatically. In fact, in the last ice age, 11,700 years ago, as the ice melted, it gives off CO2. Since the Industrial Revolution, the amount of CO2 has spiked remarkably. In fact, in the red line here on the graph, this is when we started to use modern instrumentation to measure the carbon dioxide. And it's gone up a tremendous amount, as you can see, more than in history. And we know that from studying the ice at the polar regions and looking at carbon dating. Now, it's important to look at the non-renewable energy cost in carbon dioxide. Coal is the dirtiest fossil fuel. It produces about 1 kilogram per kilowatt hour of CO2. That's remarkable. It's called dirty coal for a reason. Oil's not much better, at 840 grams per kilowatt hour of energy. And natural gas is cleaner. It's often promoted as the cleaner fossil fuel at about half the greenhouse gas emissions per kilowatt hour. But you can see the renewable, the clean energy sources, solar, hydropower, wind, are so much better for the carbon footprint. So much better, order of magnitude, going from 400 or 1,000 grams down to 28, 21, 13 grams per kilowatt hour. And nuclear, we'll see, is starting to receive a lot of attention due to AI, is also clean relative to the amount of carbon dioxide. You could argue if nuclear radiation and nuclear waste is clean or not, but in terms of the greenhouse gas effect, nuclear is right there as a clean source for global warming issues or climate change issues. Now, when you look at the amount of energy produced by region of the world today, this is 2023 in exajoules, something really stands out here. Look at the consumption of coal in the different parts of the world. And I've put this graph together where you can see the colors match up alphabetically. So you can look at these clumps of energy sources, renewable, oil, coal, gas. And you can see by part of the world what the energy consumption is. And China is a huge user of coal. It's a large landmass. It relies on the railroad transportation to move coal to the energy power plants for its population. But you can see if the world is consuming 648 exajoules per year, China is consuming about 100 exajoules, about 15% of global energy in coal. You can see the US is also using coal, if you look at the bottom blue, but we've really reduced our coal in the last 40 years. It was a government policy trying to move to natural gas, away from oil, away from coal. And you can see Europe, interestingly, Europe in green, is probably the biggest user of renewable energies compared to the other energy sources. Look at renewable energy for green, coal in green. Europe does not use much coal, uses more natural gas, and uses about as much oil as it does renewable energy. US is trying to get there. We need India and China to get there, just like the policies were put in place 40 years ago in these other countries. Now, for the last 29 years, the UN has fostered meetings between world leaders to try to address this issue. And it's called the COP, the Convention on Climate Change. And many of you may have seen the headlines just 2 weeks ago. 2 weeks ago, a lot of the small island countries in the Asia-Pacific region walked out, and Germany said that these nouveau riche countries, these countries that have grown rapidly in population, that are using a lot of dirty energy, need to put more into the effort of clean energy, because these smaller countries need to build their infrastructure to handle the rising temperatures. It was a big flap. They wanted $1.3 trillion. They got $300 billion. But the point is, this is a real issue, and the economics needed by countries to build their shorelines, to build their infrastructure, to handle the energy needs is only continuing. When you look at the breakdown of energy across the globe by industry, you see that our industry, the ICT industry, is about 4% of the global consumption. 20% of the world's energy is used in the residential world. 20% is used in transportation. You see in the US a lot of effort in the electrification, electric vehicles. That won't help if the electricity used for those electric vehicles isn't cleaner. So there's a lot of attention being paid to this. But I want to focus on our industry, the ICT industry, because this is where we can all play a part. In our information communications technology field, the power breakdown or energy consumption breakdown is roughly a third between user devices, a third in the network, and third in computing or data centers. But as you'll see in a minute, the data center percentage is starting to grow rapidly. This is going to be a huge increase, and it's going to make the ICT industry a bigger user of global energy resources. What's amazing is last year, the investment made by Microsoft, Amazon, Google, the hyperscalers, the over-the-tops, they invested more than the entire US oil and gas industry. And this is escalating. So you see the ICT industry investing huge amounts for the data center. And the question is, where will be the energy to provide these? And AI is certainly not a fad. We've heard it in every keynote. And what worries me is in all these keynotes, we have not heard about a standard metric by which to measure and compare the power efficiency of the computation or learning of AI. Yeah, it took Netflix about 3.5 years to gain 1 million customers. It took Instagram 2.5 months to gain 1 million customers. it took ChatGPT 5 days to get 1 million users. So the escalation and adoption of AI and the power consumption needs behind that cannot be ignored, and they're a huge threat for planet Earth if we don't start looking at responsibly figuring out how to quantify, compare, and drive the costs down in the energy bill. So ICT right now, you see, is about 5% of the global energy budget on planet Earth. But according to Goldman Sachs, the exponential increase in data centers, power consumption is starting to happen. And you think about the cost of power for every single ChatGPT or Google search. This doesn't include training. Training's a much higher power budget. You're talking about 10 terawatts hours. And remember, 180,000 terawatts, 10 terawatts isn't that much. But these numbers, I believe, are much smaller than what's going to happen throughout the world. In fact, a lot of the industries that are big power consumers have not been digitized. A lot of the telecom carriers and a lot of the over-the-top providers are banking on AI to help digitize, make digital twinning of industries that before really did not use much computing, such as construction or chemicals. So this is truly an impending tidal wave. And to meet the power demands, just in the last few months, headlines like these have started to appear. Headlines like 3 Mile Island to be used by Microsoft as a nuclear power plant for its AI database training centers, for its power supply. We're looking at a power plant in Georgia that was shut down to be reacclimated and to serve Google. You can see throughout the headlines, just in the last 3 months, large data center builders are looking to nuclear for their power source. What's also, excuse me, what's also pretty interesting is around the world today, these hyperscalers have already been locating their data centers at natural gas supply lines. You can see that all the build-out of the data centers are happening at natural gas depots. That's happening globally. So there's a tactical effort to get the energy to drive the huge power budgets that AI is going to bring. Yet with a problem this big that we all face, I'm surprised, and I hope you would be surprised, at how many different disparate energy efficiency metrics exist. Just in our own field, in the field of circuits, in the field of data centers, in the field of wireless networks, radio access networks, and AI/ML, which I don't think even has an energy efficient metric yet. I want to show you some examples of just how disparate we are as engineers in trying to quantify energy efficiency. Take a look at RF power amplifiers. There's 2 well-known metrics for power efficiency. It's called power added efficiency, equation 1 and equation 2. For low noise amplifiers, there's yet a 3rd metric, which uses its own figure of merit. If you look at data centers have a figure of merit called the power usage efficiency, which attempts to break out the energy or the power consumed by the information technology and the auxiliary power and cooling, the non-infotech. This is a common metric. And you could have data centers of different sizes have the same power user efficiency metric, which is fine if it's really telling you power efficiency. And then just look at our wireless industry. ETSI, ITU, 3GPP. There's different energy efficient metrics for the base station, for the network, for the RF unit, for the application. So many different power efficiencies. And just recently I learned about another one. IEEE is working on its International Network Generations Roadmap, trying to define yet another power efficiency metric. So what's an engineer to do when faced with a major problem and a major opportunity to help planet Earth? And there's all this confusion, all these different areas. Well, something I've done in my career, every 6 or 7 years, I take a vacation and I go back and I read the papers by Claude Shannon and Warren Weaver and Harold Freese. And if you haven't done this, it's really, every 6 or 7 years, I encourage you to do it, because whatever's happening in our world now, it's just nice to go back to the 1940s when the whole field of information theory was not yet here, our industries didn't exist, and to see how these people at Bell Labs thought. And when you read these people, you see that Claude Shannon is kind of like a Monet or a Renoir. He paints with all these brush strokes, and he has all these theorems and these beautiful ideas that are all across the canvas. Harold Freese is kind of like Jackson Pollock. He throws some paint on, takes a blunt instrument, and he puts it right there. Harold Freese's papers were very short and succinct. He created noise figure. He created the path loss equation in free space. Claude Shannon created numerous things, information theory being just one of them. So I was a professor in 2008, and I had this brilliant undergraduate student, James Murdoch. He came to me as a graduate student after doing an undergrad at Texas, and he wanted to solve a perpetual motion machine. He wanted to make a zero-energy computing machine, a Turing machine that did not consume energy. And he spent about 5 months trying to figure out how energy is lost, the law of thermodynamics. He was trying to figure out if it could be done. He came back, he said, I can't do it. There's always loss. And I said, well, why don't you go read these papers by Shannon and Freese? Because they were dealing with this in the 1940s, trying to figure out how to make sense of communication. And he went back and he read these papers, this paper by Shannon, which brought us information theory. You can see what Shannon talks about is the definition of entropy. And entropy came from the work 70 years earlier by Boltzmann. Boltzmann was looking at molecules. We hadn't discovered the electron yet, but in the 1870s, he was looking at how gases and fluids change, and he wanted to get to the basic state, the lowest part of information of how a molecule moves around and how a gas changes state. And this is where Shannon got his H entropy formula from Boltzmann's H in the 1870s. And the entropy basically broke it down to the phase space, the smallest possible part of information that was known about fluids. And that's how he came up with the definition of bit, binary digit. Binary digit was the smallest, the most basic possible phase space of a communication channel. This led to information theory. And at the same time, Harold Freese was looking at the amount of noise in a wire. What do electrons do just sitting there due to thermal agitation? And in Harold Freese's paper in 1944, you can see he's looking at the Johnson noise, which is just the noise that was measured in 1926 in Bell Labs, the noise of electrons, and this is where the KTB comes from that we use for noise power in signal-to-noise ratio. So James Murdoch looked at these papers and he got very excited about a month later, because after reading Harold Freese and Shannon, he realized that we could look at wasted power in a communication system just the way Shannon and Freese looked at information. Now, Gerhardt made a good point that Shannon's capacity theory only looks at the energy per bit, doesn't look at the energy per system. Thank you so much. Appreciate that. And what we see in these papers by Shannon and Freese is also a cautionary tale for the semantic communication we've heard so much about. And I agree so much with Richie. Richie's point is we have to figure out a theory for the amount of information in semantic communication. If we don't have a common theory, we won't be able to break down and create a scalable set of laws for the emergence of AI. Just like we have all these different energy efficiency metrics today in our field, there were all kinds of different thoughts going around till Shannon and Fries put together the theory of information and came up with a way to model noise and a way to model the noise figure, the noise carried through a system. So in 2011, James Murdoch, having looked at Shannon and Fries, came up with consumption factor. He was so excited. We wrote a couple papers about it, really went undiscovered. And we're trying to figure out how to measure wasted power in a cascade, wasted energy in a cascade, because there was no formal way to do it. And the key breakthrough was if you look at any source in any sink, it could be a single-dimensional or multi-dimensional source and sink, you have a signal path, that is where the information goes from left to right, and then you have all these ancillary components, a display, heat sinks, that are not on the signal path. And if you break any communication link into these two disparate paths or components, you can use superposition to find the energy consumption. And we did this by looking at the energy consumed in a communication system, and we were able to figure out the energy consumed per bit, not just by Shannon, but by bringing in the idea of this consumption factor. Now, we were messy with the notation. Today, we call it the waste factor, and it's actually a reciprocal of this value H that appeared in this 2014 paper. But the bottom line is we now had a theory that allowed us to quantify energy consumed in any source-to-sink link of any kind. And I had kind of forgotten about it till Nokia came to us to try to figure out what's more efficient in a high-altitude platform. Should it be a bent pipe repeater, or should it be a base station, which actually does reception and retransmission? And I want to make a point here for the audience, because a lot of people are young and don't realize that the field of RIS, reconfigurable intelligent surfaces, is not new. 40 and 50 years ago, we called these repeaters. And RISs are simply repeaters or relays, which have intelligence and are modern, but don't miss the fundamental contributions on repeaters and relays. And we looked at used the theory to figure out what's more power efficient on a link. Do you use a base station or a repeater? And this kind of revived the interest. And since then, we've figured out the notation, and we call it waste figure and waste factor. And it's very elegant, and it's very easy to use. And the good news is we can use it on MIMO, massive MIMO, and as I'll show, data centers, circuits. It's a unifying method for quantifying the energy efficiency of any communication system. And here's how it works. This parameter W is simply the consumed power over the path from source to sink, divided by the power that's in the useful signal at the output. Look at the equation below this big box, and if you put in the numerator P consumed and make it P signal out plus P non-signal, it's basically saying W, the waste factor of any system, is simply the useful power that gets out plus the wasted signal that gets out divided by the useful signal that gets out. And if W is 1, it means there's no wasted power. All the power used in the system goes into the output signal. If W is infinity, it means no signal comes out. It's just like noise factor for thermal noise, but now it's waste factor for wasted energy or wasted power. And the beauty is, following Fries mathematics, it's identical to what we use today in all our textbooks to compute noise figure. It's based on the waste figure of each component closest to the output divided by the gain of the previous stage. So this gives us a very efficient and easy way to quantify energy consumption in any communication system. And so just like in 1944, Harold Freese gave us noise factor, we have waste factor, which is referred to the output. And it works just like noise figure. For a resistor, the waste factor is simply the power out divided, or it's the total power divided by the total out. In other words, the total in minus divided by total out, which is just the loss. You can see here that W, which is 1 over efficiency really, is simply the non-signal plus signal divided by signal, which is just the insertion loss. So in waste factor, a resistive attenuator has a waste factor that's equal to the loss, just like in noise figure, the noise figure is equal to the loss. And the beauty of this is you can now look at, say, a homodyne transmitter where you have a signal path, it goes through mixers, filters, and you have off-component paths, things that are not on the signal path like oscillator, and you could very, very rapidly, very easily compute the waste factor for the entire system from source to sink. And I won't go through the math, but the bottom line is it's just like noise figure. You can actually choose the most power efficient design for the different components. And unlike noise factor, which Harold Freese did just for receivers, this also works for channels. As long as it's linear, you can also have a waste factor for channels because it's lossy. And by doing this, you find out there's some fascinating properties in a transmitter, channel, receiver that allow you to very rapidly figure out the total power consumed, and it allows you to trade off the noise figure or the waste figure of the receiver, the distance and the loss in the channel, the transmitter waste figure. It gives you a whole range of flexibility, just like we had when Shannon and Freese developed their theories. And this also works in circuit design. Waste factor is a unifier for circuits. No longer do we need different values of PAE. We can use W to relate to the old metrics, and we have a single quantifier, waste factor, for the different PAE definitions. And even in data centers, if you look at data centers, which are huge consumers of energy, let's take an example. These two data centers are different sized. They each have a power usage efficiency of 1.833. But if we go to the principle of Shannon, which is to get to the basic state, to get to the bit, the first fundamental part of information, we can start breaking down what's in that data center and look at the part of energy consumed on the source to sink path in the data center. We'll call that the information flow. And then we can look at the wasted power that's not in the information flow, but vital for information, namely the processors in memory, the NIC cards. And then we could look at all other components. And when you do this, you're able to break down the constituents of power consumption much better. And you can see where the energy use is greater and has bigger impact. When we do that, you see that the PUE metrics said they're the same, but using waste factor, you see that the data center A, which consumes more power, is a greater energy consumer, is actually more efficient. It is a lower value of W for the information flow, which means you could then focus on lowering the energy in other components of the data center. Now, here's an example in our radio access networks, and it's work we did with Huawei. Huawei's embraced this and has been using this, and other companies are starting to look at it as well. Let's consider two base stations. Let's say the green one is a new one, a 5G radio, and base station B is an older 4G radio. 5G has been made more power efficient in the standard and with better components. And here we're going to look at the energy efficiency metric defined by one of those many ITU metrics. In this case, it's ITU L1310. If you look at the ITU spec, both of these base stations are equally energy efficient. However, if you use the waste factor to consider the amount of energy being delivered over the channel versus the amount of energy being consumed, what you see is the newer base station has a lower waste factor and is actually about 15% more energy efficient. And the key is that these metrics don't consider the fact that there's on-path and quiescent components all being lumped into their metric. If you break it down to the basic phase state, what you see is that the old way of doing things is very much dependent on the loading. It's very much dependent on what's happening with the traffic. But with waste factor, you're able to remove that and keep track of the path independent of the traffic loading. And this is really key. So one way to think of this is with this parameter W waste factor, the optimal case will be have a very low W, as close to 1 as possible, with very high data rate. That's an optical carrier situation. Or we might have low data rate, and when we have low data rate but low waste factor, that means things are good. We have a low waste, we're not wasting energy, but we can now boost the transmitter and, or expand the bandwidth to get more data through. If we have high waste factor, which is bad, but we have high data rate, we're satisfying the customers, but we're wasting energy. We can actually replace the radio unit with a more energy efficient product with lower waste factor. And then finally, we could, with a high waste factor and low data rate, that's the worst of all worlds, we need to replace the infrastructure, move to smaller cell size, and possibly use RIS. So this is all covered in a paper this year in the Open Journal of Communications, but it's really based on some of the early principles that led to this information theory and led to our world, and we need a standard metric. We need a way by which all of us can compare the compute power of AI or see what our algorithms are doing in terms of planet consumption. So let me conclude by saying we're facing a true tidal wave in energy consumption. It's going to affect all of us, all of our children, and we lack a unified figure of merit for energy efficiency. We've used the fundamental laws to determine waste figure, and we need a similar metric for understanding the computations used for training and using of AI. Thank you.
Thank you, Ted. Are there any questions that anybody wants to raise? Yes, sir, please go ahead. Yep, yes.
So thank you very much for the bringing up the concept of energy efficiency, which we all agree is very important in addition to the block error rate, the error performance. So I was wondering that in your decomposition of this energy consumption, do you take these, the formulas for the waste factors, the consumption in each modules, do you take it in empirically, or do you have an analytical way, just like what Shannon did, to derive all this energy consumption based on theory only?
Yeah, the beauty of waste factor, just like the beauty of noise factor, is that it can be measured. So you can actually measure it. We showed it's simply the total power consumed divided by power out, or you can model it, which is how the original work was done. So you can do both. And you can use Shannon's theory, and I show it in one of those papers. Shannon's theory can be used to figure out the capacity with the energy being used in waste factor. So that's a key. You need to be able to measure it and model it. And that's what we need in computing.
So we take both approaches.
You can use either approach.
Okay.
Both are valid. Same answer.
I see. Thanks.
Yep.
We'll take one more question there.
Hello. Ted Deepmedi from NSF. I have a question for you. It's great to hear about the waste factor and everything. My question is slightly different. What are we missing in our undergraduate and graduate education that we need to train our next generation of scientists? Thank you.
I love that question. Thank you, Deepak. It turns out I'm teaching first-year students for the first time in my life. I taught them last year. The dean said, we need to keep them through senior year. You go teach the freshmen. I've been so inspired because what I found is, and one of my PhD students, Debankar, told me this. He said, you don't know where you can go unless you know how you got there. And so I'm trying to inspire first-year students by showing them the history, actually telling them about Shannon, and telling them about Boole, the professor who invented Boolean logic, showing a little bit of history, how we got to where we were, show the community of researchers how they used to get together. You know, like Pierre Laplace used to have all the mathematicians at his house in France, and that's how Babbage, a young professor at Oxford, came to learn about the logarithm tables that had been developed in France, and that's how we got the idea to make a difference machine. I try to tell them these kinds of stories to see that they too could be inventors. They too could look at the shoulders of giants and take those lessons learned. And so I give them 15 lectures, 15 groups of homework problems with a little bit of math and the history. That's what I think we need to do. We need to give the undergraduates some courage that they could be just like everyone else who created the world they live in.